file name, then open that folder. In that, open in terminal. Invoke the tool, Cadence tool, by giving the instructions command csh and source cshRC file. It will open the Cadence tool. Then invoke full custom tool by giving the command VIRTUOSO space ampersand. It will invoke the tool. Once the CDS log file is open, you have to create a library for putting all the schematics. Let me give the library name as test. Then attach the library to the technology file or technology library. That can be done by choosing the third option, that is attach to an existing technology library. Then say OK. Then here you need to choose the required technology file using the scroll down option. We are choosing GPDK180. Say OK. Once it is done, that will be displayed here in the CDS log window. Design library what I have created is being successfully attached to technology library. Now we are ready for creating the schematic. That is, to create the schematic, enter into this library manager and see whether the library what you have created is available under the libraries of the this workspace. Just see that the name of the library what we have created is test. Is it available here? Just check whether your library is available under this libraries. Test is created. As I have not created any schematic here, the second column and third column are empty because none of the circuits are drawn with any of the views. Therefore, it will be empty. Now you start with the first schematic, that is file new cell view. To create the schematic, if I click on that, it will open a new file form. Here I need to give the name of the file. If I am doing NAND gate, I will give the name as NAND, and the view of the NAND gate is schematic and the type is schematic. If I say OK, it will open a blank schematic window. In this blank schematic window, we need to draw the schematic. For drawing the schematic, I need to take the components. To pick up the components, there are three options. Either we can use create instance menu option, or we can use this just by clicking on this icon, we can get the same create instance option, or the short key I, that is from the keyboard I, if I press, it's going to open the add instance form. Browse here for various libraries and pick the required components. In the library browser window, you click on GPDK180 where the transistors are available. Select nMOS and view of that should be symbol. Say close. Once I close, it's going to open add instance form where I need to edit the property. For this schematic, I am going to choose the transistor width as 1.7 micro and length let it be 180. Then say hide. I need two such transistors for NAND gate. I am going to place 2 times. After this, the same procedure I am going to repeat for picking the pMOS transistor, and pMOS transistor width I am going to choose as 1.275 micrometer. Then I'll hide this form. Then I'm going to place this pMOS transistor 2 instances. Then after this, I need pins for applying the inputs as well as applying the VDD and VSS and for observing the output. Therefore, I'll pick the pins. For that, once again, we have 3 options. Create pin. This is the menu option. Or I can click on this icon which is there in the taskbar. Or I can use the short key P. If I use P, it's going to give me the same thing. List all the pins at one shot which are in the same direction. We know VDD, then VSS and A, and B. These are the inputs, and these should be selected in the direction input, say hide. Now you need to place in the same order. VDD should come at the top, then VSS at the bottom, then A and B inputs at the left hand side. Then finally I need to take the pin for output. Once again I'll execute P. Then I am going to choose the output name as Y. Then change the direction of this pin to output because it is the output pin. Hide and place it in the right hand side. Now we are ready with all the components. You need to make the required connection as per your circuit. For that I need wire. For taking the wire, once again we have three options: create wire narrow, or I can click on this icon, create narrow wire, or I can use short key W. If I click on short key W, complete the wiring as per the schematic. That is, drain and drain of pMOS are to be shorted. Then source and source of pMOS to be shorted. Then from this shorting I need to connect to drain of nMOS, and from the source of first nMOS to drain of the second nMOS, and source of second nMOS to VSS. Then here body of pMOS should be connected to VDD, and second transistor's body also should be connected to VDD, and the shorted drain should go to VDD. Then body of nMOS transistors are to be then apply the inputs now. Pin input A should be applied to one of the pMOS transistor gate, and another wiring should go to nMOS transistor gate. Now I have applied first input. For the second input, once again I need to apply the second input to one pMOS and one nMOS. That is done through this connection. Now the connection is complete. Now I need to verify whether it is working as expected. For that I am going to click on check and save. If I click on check and save, if everything is correct, it's going to be displayed in VIRTUOSO log window. You can see here schematic check completed with no errors. If there is any error or warning, then you need to debug those warnings and errors. Now we are done with schematic. Now this has to be converted into a symbol, so that I am going to generate a test schematic. For doing it, execute this, create cell view from cell view. If I do this, it's going to open a new form which is named as cell view from cell view. Here you need to ensure it is in your library only, and cell name is proper, and from view name is schematic, and to view name is symbol. That means I am converting from schematic to symbol. Say OK after verifying this. Then it's going to open symbol generation option window. Here it is showing left pins are A, B, VDD and VSS, but as per my schematic, VDD should be at the top. Therefore I am going to select this, cut this, and I am going to place that VDD at the top location. Then VSS, as per the schematic, it should be at the bottom. Therefore I'll cut that, and I am going to paste it in the bottom pins. Now if I say OK, it's going to show general symbol, which is going to be standard symbol, which is going to be created by your tool. If you want to customize it, we can do the customization as per the requirement. For customizing the symbol, you have to delete these two rectangles, then customize this. For customizing this, create shape line. If I do, it's going to create a line. After this, I am going to use create shape arc. from there to, then from here back to this, then I am going to just say a circle to indicate it is a NAND gate. This is the customized symbol for NAND gate. Check and save. Then after this, close this window as well as this window. Now we are ready with the circuit which has to be simulated. Therefore, create one more circuit now for testing the circuit schematic which we have drawn. That can be done by executing file new cell view. Then here it is. Ensure that it is in your library. Then give the name of the cell as NAND underscore test. I am generating a test circuit, or I am creating a test circuit for a NAND gate. Say OK. Then it will open a blank schematic window. Pick the required components. Once again the same procedure. Create instance. If I click, I have to browse, and the NAND gate symbol is available in my folder, that is test, and pick that symbol and place it here. That is the first component we need. After placing the NAND gate, then take other components like I need DC voltage for VDD, and I need ground for VSS, and I need V pulse for A and B. I am going to take that with the same procedure. Create instance. Then VDC is available in analog lib. I will be taking that here. The name of the DC voltage is VDC. I will click on that. Then I am going to close. Then I will be setting the value of DC voltage as 1.8. Only the numerical value of that voltage you need to give. No need to give the units. Simply say hide. Then I am going to just rotate this and I will be placing at the top. Then I need ground. For that, once again create instance. Ground is available in analog lib only with the name GND. I'll take that. Then I'll place that ground as many times as I need. I need here, then I need here, and I need for 2 inputs. Then after this, I'll take the pulse, V pulse, that is voltage pulse, for applying the inputs. It is named as V pulse, and I need to set the properties. DC voltage 1 is 0 volt and DC voltage 2 is 1.8, indicating this that logic 0 is 0 volt and logic 1 is 1.8. Then I am going to set the period for that. Let the period of this be 10 nanosecond, and rise time let it be 1 picosecond and fall time 1 picosecond. Then pulse width for this, okay, 10 nanosecond. Period I am going to make it as 20, double the pulse width. Then I will hide it and I am going to connect it to input A. Then one more input V pulse I need, and I am going to place it here. But for this I need to increase the width of pulse and period, so that I am going to get all the 4 combinations 00, 01, 1011. For that I will edit the properties of this. It's going to be 0, 1.8 as it is. Period will be, now it is 40 nanosecond and pulse width is 20 nanosecond. It is twice that of the previous one. Then say OK. Then finally I need a capacitance for the output. I'll select the capacitance from analog lib, and the name of the capacitance capacitor is named as CAP here, and pick that and choose the value of that 0.1 picofarad. Hide and place it at the output end. Then complete the connections as given in the circuit, that is using the option wire. Create wire from VDD to positive of supply voltage and negative of supply voltage to ground, and output Y to one end of capacitor, at the other end of capacitor to ground, and VSS to ground, and pin A to positive of V pulse and negative of V pulse to ground, and pin B to positive of V pulse and negative of V pulse should go to ground. After making these connections, now you just label the wires with the option L. Then I am going to give name as A, that will be given for this net. Then one more labeling I am going to do, that is for B, and that will be labeled for the second wire, and third labeling is for the output, that will be given for the last net. When you are connecting, ensure that none of the connections should come within the boundary which is shown in the dotted line here. Otherwise, during simulation, you are going to get errors. Then after this, check and save the design so that you are going to verify are there any connection mistakes while making the connections or any other errors. If no errors are there, you can see that in the VIRTUOSO log window. Open that and you can see schematic check completed with no errors. Which is that schematic which is being checked? First word is your library, that is test. Second word is the cell name NAND underscore test, and third word is schematic, it is the view name. Then once it is done, now start with the simulation. For simulation, you have to launch a subtool by name Analog Design Environment, that is executed like this: launch ADEL. If I click on this, it's going to open ADEL window. This is the ADEL window. Here make the necessary setup. Very first step is you need to go for this setup and check whether model libraries are appropriately selected. That is GPDK 180 should be selected. If it is selected, say OK. Then choose the analysis. First analysis I am going to do transient analysis, and as I have taken 40 and 20 as the cycles, let me choose 100 nanosecond as the pulse width so that I can visualize at least 2 cycles of the input. Then select the accuracy details as moderate and say OK. Now this setup, what I have done, is going to appear in the analysis field. That is, type is transient analysis. It is being enabled and it is going to be done between 0 to 100 nanoseconds. Then after this, outputs what I am going to plot will be selected by executing this. Outputs to be plotted, select on design. Outputs to be plotted, select on design. If I click now, it will take me to the design window. Select what and all signals you want to observe. I want to observe A, therefore I'll click on this. Then I want to observe input B, I'll click on this. And I want to observe output Y, I'll click on this. Then I'll press escape so that that selection option is disabled. Then I'll come back to ADE. In the ADE window, now we can see in the outputs form or output field, all the 3 signals which are being selected will be displayed. Simulate the test schematic by giving the executing netlist and run. We get the results. Here, to calculate the delays, open the calculator. In the calculator, select delay function. Then clear buffer and stack. Then signal 1 has to be selected from waveform window, that is A, input A. Signal 2 is output. Select output. Then switching threshold is 0.9, that is half of VDD. Then observing here, the input is falling, A input is falling, output is rising. We'll consider the delay for the first edge, that is first falling edge and first rising edge. That is, edge number is 1 and edge type is falling for input and rising for output. That is because we are considering the delay between these 2 edges now. Then apply this and evaluate the buffer. it's going to show the delay as 36.6 picoseconds. Then for the remaining 3 combinations, we need to compute the delay. For computing the delay, that is, we need to consider this edge now for the input, and output has to be considered for this. And for this edge, it is rising, and it is first rising edge. In the output, this is the first falling edge. Therefore, the edge number will be 1 1 only, but the edge type is, it is first rising edge and first falling edge in the output. Clear the buffer, apply this, then evaluate the buffer. Then it's going to give the delay as 155.3 picoseconds. Then for the remaining 2 combinations, to calculate the delay, observe the waveforms here. This edge and this edge we need to consider. This edge, that is edge number 2 of falling kind. This is the first falling, this is the second falling. Whereas in the output, we have to consider the respective edge. This one, this is rising, and it is edge 2 of rising type. Therefore here we need to consider, make this edge number as 2, and edge type for input is falling, and edge type for output is rising. Clear the buffer, apply this, and evaluate the buffer. It's going to give the delay as 122 picoseconds. Finally, for the last combination, if you observe, this edge we need to take in the input, that is rising, and it is second rising type, rising edge. Whereas for the respective output, if I consider this edge, we need to consider, that is falling. In falling type, it is the second type, second edge. Therefore here in the setting, we need to consider the edge number as 2 itself, but the edge type for input is rising, whereas edge type for output is falling. Clear the buffer and apply the input to the buffer and evaluate the buffer. It's going to be 89.4 picoseconds. That's why we can see now 4 different delay values, that is 36 picosecond, 155 picosecond, 122 picoseconds, and 89.4 picoseconds. This is the pre-layout values. To draw the layout of NAND gate, open the schematic and make the changes of properties of pMOS and nMOS transistor width as pMOS should be set as 40 micrometer and nMOS width should be set as 20 micrometer. Then check and save. Okay, now after this you need to launch the layout Excel to draw the layout. As I've already drawn the layout, it is showing, can I open the existing one? Just say OK. Then it is going to open. Once it is open, it's going to be appearing like this. That is, to draw the optimized layout, what I've done here is pMOS transistor and nMOS transistor. I've taken the properties. Open pMOS transistor properties and make these changes. That is, consider the width of pMOS as 40 micrometer. Now to draw the layout, what I am doing is, the total width of the pMOS is divided into 20 blocks by making fingers, number of fingers as 20. If I take the number of fingers as 20, then finger width should be 2, so that 20 into 2 becomes 40 micrometer. Then body type of this, I am going to set body type as integrated, and I will be using the tab for body or as left tab as well as right tab on both the sides of your transistor. You can see the tab for body. That is what the meaning of selecting left tab and right tab. Then say OK. Same thing has to be done for the second pMOS transistor. That is, number of fingers is chosen as 20 and finger width is chosen as 2 micrometer, so that put together it becomes 40 micrometer, 20 into 2. Then body type, you need to select it as integrated, then left tap as well as right tap. That is, I am going to connect 2 taps on the extreme ends of the transistor. That is what the meaning. Then after this, come to nMOS transistor. In the nMOS transistor, same thing, number of fingers I am going to choose as 20, finger width is 1, so that totally it comes to 20 micrometer. 20 into 1 results in 20 micrometer. Then body type here, as one of the transistor is connected to, body is connected to source, and other transistor body is connected to source, and source is not connected to VSS. I am going to take detached here. Once I take detached, body and this source will be detached, and I am going to have these tabs on both the sides. Say OK. Then do the same thing for the next. That is because here you can see the body of this is connected to VSS, but the source is not connected to VSS. Hence it is, both of them are at different potentials. Hence I have taken detached body type. For this I can take either integrator or detached. I will take detached itself. Properties. Then here number of fingers 20, finger width is 1, so the 20 into 1 becomes 20 micrometer. That is the total width of nMOS transistor. Then body type I will be taking it as detached for this also, and I am going to put 2 taps at both the ends, right tap and left tap. Say OK. Then after this I need to invoke the layout editor. For that, launch layout Excel. If I say, if you are drawing it for the first time, it's going to create a new one. As it is already drawn, it is going asking shall I open the existing one. Say OK. Once you say OK, it's going to open the existing one. See, if it is not drawn, this will not be there. Then blank window, layout window will be there. In order to create the layout for these basic primitives, what we are supposed to do is just execute these steps. Here already it is drawn, therefore the steps I will be explaining. What you are supposed to do is, first step is connectivity, generate all from source. If I say connectivity, generate all from source, the meaning of this is I am going to generate the layout for the basic transistors. That is, there are 4 transistors, and pins, there are 5 pins. The tool itself will generate it from the source. Source is the schematic. Then if I say OK, it's going to generate all these layout. That is, here I am highlighting those things. This one, this is the layout of pMOS, this is the layout of second pMOS, this is the layout of third pMOS, and this one is the nMOS transistors, these 2. Then after this, you can see number of fingers here. If you count the green lines, there will be 20 lines indicating the number of fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 fingers. Same thing for other transistors also. And if you zoom and see here, you can see this source and body are connected together here on the left hand, similarly on the right hand. And if you treat this end as source, obviously other end of this finger becomes drain. For the first finger, left hand side is source and right hand side is drain. For the second finger, as this is already drain, this end has to be source. Hence for the second, that is second finger has left hand side as drain, right hand side as source. For the third one, left hand will be the source and right hand side will be the drain. Like that it goes for pMOS. Similarly, for nMOS, if you consider, here this is the nMOS transistor layout. You can see body is detached from the source. This is the body, this is the source. And for the right hand side also same thing. This is the source end and this is the body end. And for the second transistor also I have taken the same thing. Now, in order to understand the circuit connection, just refer the schematic. If you refer the schematic of your NAND gate, it looks like this. That is, both the transistors drain, source end. For pMOS transistor, source end has to be connected to VDD. I'll open this, and if, as I've already mentioned, these are the source end. This left hand side of first finger, third finger, fifth finger, like that, and right hand side of second, like that. It goes for there will be shared regions. Hence you can see from this end I am taking a metal line to VDD supply. Similarly, after this becomes the shared region which has to go to drain. Like that I am going to make all these drains. That is, for all the fingers I am going to have the drain end to be connected to source end to be connected to VDD. Similarly, for the second transistor also, all the source ends of pMOS transistors are connected to VDD. Then if I go for nMOS transistor, if you observe the schematic, bottom transistor source end should be connected to VSS, and the body of that also should be connected to VSS. Top transistors, only the body should be connected to VSS. That's why here, if I assume this is the bottom transistor, only body should be connected to VSS. That's why detached body is taken to VSS, whereas the top transistor, all the source as well as body should be brought to VSS. See, this is the body which is connected to VSS using metal line. This is the source which is connected to VSS through metal, and other source regions I am taking it to VSS, and the extreme right end I have body as well as source which has to be connected to VSS. That is, I have completed this connection now. That is, this body and the body of the second transistor and source all are connected to VSS. That is done here with this metal connection. Then explanation of this is also done. That is, the source end of pMOS transistors are supposed to be connected to VDD. That is done through this. All the source end is connected to VDD. Next is, if I take the drain end of this pMOS transistor, drain end of this pMOS transistors, they are shorted, and in order to make that connection, see here, this is the, if I zoom here, we can see here, this is the drain end of pMOS transistor, and bottom transistor drain is here. Therefore I am shorting those two drains using this metal connection, what I am highlighting now. Same thing has to be done for remaining fingers. Drain ends of all the P and first P and first nMOS transistor are to be connected, and that is done through these connections, blue lines, okay, blue polygons. Then after this is done. That is, drain end of one transistor is connected to drain end of this nMOS transistor. Similarly, drain end of this should be connected to the same point. That is done with this. Supposing if you observe the drain end of this, just I'll zoom and I'll show. This is the drain end. Drain. I'm extending a drain, and from there I am running a horizontal metal so that I'll connect the drain of this to shorted drains of these two. That is done with this horizontal metal line. Then after this, we have the drain of bottom transistor, nMOS transistor, should be connected to source of top transistor, nMOS transistor. For that, what I am doing here is, I am taking the source ends. See, this is the source end of bottom one end top transistor. This is source, this is also source. Like this, I am extending all the source using blue wires, and here drains, that is, here this is the drain end of this also I am extending, so that all the drains are extended. Now I am supposed to short these two, that is, source end of top transistor to drain end of bottom transistor. That can be done by running a metal. Supposing if I run a horizontal metal line here in the using metal 1 only, there will be a wrong connection at this point also. Therefore, in order to avoid that, I will take metal 2, which is shown in red color here, and I will run that metal 2 from here to another nMOS transistor's drain. That is, all the shorted all sources are shorted, and that is connected to all the drains here through this horizontal red color wire. After this, metal 2 and metal 1 will be at different levels when you consider the cross-sectional view. Therefore, in order to make connections at the appropriate point, I am going to use appropriate via. In order to connect this metal 1 to metal 2, I'll execute this. That is create via. If I take, it will ask which via you want. I'm going to take metal 2 to metal 1, and that will be placed at the appropriate place. That is, here this source should be connected to this drain, means here there is one connection required. Therefore, at the appropriate ends, I am connecting metal 2 to metal 1, so that this connection is completed. This one, this source end of top transistor to drain end of bottom transistor. Once it is done, now your connection or layout looks like this. I have done the connection for nMOS transistor as well as pMOS transistor. That is, now this end is has to be connected to output Y, and the gate for pMOS and nMOS are to be shorted. That should be connected to one input, and second pMOS and nMOS are to be shorted, and that should be taken to the second input. That is done finally here. See here, I am running a horizontal poly here, and pin B I am placing here, and pin B is in metal, and this is a polysilicon. Therefore, two different layers, I need to connect them. How do I do it? I'll go to create via, then I'll select metal 1 to poly 1, and I'll that poly contact I'm going to take, and I'll be placing that here, so that that polysilicon is getting connected with the pin which is named as B. Same thing is repeated for this also. All the polys here are shorted through this horizontal poly wire. Then that pin A corresponding to second input will be placed on this. Once again I am going to put one more via metal 1 to poly 1, so that it is getting connected here. Then after this, this is your VDD rail, pin should be there on that, and this is VSS rail, VSS pin should be there on that. Finally, the shorted drains of 2 pMOS and 1 nMOS are to be placed with pin Y. That is done here. This is the pin Y. Then this completes all the required connections. Then your layout looks like this. Now after completing the required connections, it looks like this. It requires a metal 2 for avoiding the connections, unnecessary unwanted connections. Then after this, you are supposed to verify whether it is as per the design rules. For doing that, the first step is you are supposed to select the GPDK file which is in a particular path. For that, Ashura technology, if I click, as it is already set, it is showing like this. Otherwise, you need to browse. Once you browse, you have to go to required path. Required path is, go back like this. First folder is home. In that, under that you have install, under that you have foundry, under that you have analog, under that 180 nanometer, under that Ashura _ tech.lib. This is being selected, then say OK. Once it is done, now you are ready for the design rule checking. Execute this Ashura run DRC. If I say like this, initially if it is the first run, it will be something like this. It's going to be technology will be undefined. Then you need to set it to GPDK 180. Set this, then say OK. Then after giving OK, it's going to run the DRC, and if any errors are there, you need to debug. I'll see the results here. There are no DRC errors. That means it is through with the DRC. Then the next step is, after checking for the design rules, we go for the layout versus schematic check. That is done with Ashura run LVS. LVS stands for layout versus schematic. Click on this. Then once again, initially it will be in undefined. You just make it as GPDK 180 using scroll down option. Then say OK. Then it's going to be, it will run the LVS, and if there are any mismatches in any pins or any instances, it will show. Otherwise, if everything is matching, it's not going to show any errors. Once the LVS is it's in progress, once it is done, it is going to show the LVS report. that LVS report will be something like how many pins are mismatching, how many instances are mismatching, and how many nets are mismatching. If no mismatches, then it's going to show 0 mismatches, and finally the result will be layout and schematic match. If that is done, your LVS is through. Then DRC and LVS are referred as physical verification. Drawing the layout is physical design, and in order to verify that, you are going to execute these two steps, DRC and LVS. If you do those two, then you have verified your physical design. Once the Ashura LVS is done, still it is in progress. Once it is done, it is going to show it is LVS result. The result of LVS looks like this. As you can see here, it is showing 0 cells have 0 net mismatches, 0 cells have 0 device mismatches. As everything is 0 here, no mismatches. If I say yes, it's going to show LVS debug environment window here, where you can see schematic and layout match. If you get this display, it's understood that layout is perfectly matching with the schematic in terms of devices as well as in terms of pins as well as in terms of nets. Then we can proceed for the next step. In the next step, I am going to execute RC extraction. For that, Ashura run quantum QRC. If I click this, it is nothing but I am trying to extract the R and C, parasitics, resistance and capacitance of my circuit. That could be done like this. Once the RC extraction run form opens, if you observe the first tab, it is setup tab. It is showing output will be extracted view, and it is going to be available in the cell named as AV extracted. Then after this, go to the second tab, extraction tab. Here usually it will be in C. You need, that means it's going to extract only capacitance. You need to extract both R and C. Therefore select RC using drop down. Then give the reference node. Initially it will be blank. Now reference node should be, supposing if I use VSS, that should be here, or if I have named that as ground, that should be here. That means here if you go here, whatever the name I have given for this pin, that should be the reference node. Then after this you say OK here. If I say OK, then it's going to run the QRC for this, and once it is done, it's going to show the result in the AV extracted window. The result of RC extraction is shown here. It is displaying. It's going to be available in the view AV extracted under your library. Close it, and if you go to library manager now, for your cell, one more new view is created, that is nothing but AV extracted. If you just open that, you can see the R and C values associated with your circuit. See, it will be something like this. Zoom and try to see. If I just zoom some portion of this circuit, I can see R and C. Shift F if I give, it's going to display. Parasitic capacitance. This is the parasitic capacitance which is being extracted. It is going to represent one of the parasitic capacitance in your circuit. Usually it will be a small value. Similarly, you can see the parasitic resistance also. This is one of the parasitic resistance which is shown here. Like this, there will be so many resistance, parasitic resistance and capacitance associated with your circuit, which has to be taken back to your simulation and do the post layout simulation, so that you will come to know exact delay including all these RC values. See, whenever you open any window, you just ensure that you have opened the appropriate one. That is, this is your library, first word, second one is the cell name, third one is the view name, AV extracted. For post layout simulation or back annotation, what we are supposed to do is first go to a test circuit which has your layout. That is, in my case it is NAND underscore test is the test circuit, and this is the library. You just execute file new cell view. If I execute file new cell view, then it is going to open new file form. Here I need to change the type as config. That means I am creating a new configuration for my schematic. Say OK. Then it's going to open new configuration window. Here library is my library, then the cell is NAND underscore test. Then here you need to select the view as schematic. Once it is selected, global bindings are not yet filled. In order to fill this, click on this use template, then just say spectre, then say OK. If I say OK, these things, global bindings will be filled. Then after this, if I say OK in this, it's going to open one more window, that is hierarchy editor, new configuration window. Here you can see there are two views, hierarchy editor window, where you can see you are designing two views. One is table view, where you can see in the form of a table all your schematic information will be displayed. Whereas second one is tree view. Here once again in the form of hierarchy, tree like structure, you are going to see your design. Click on this I0, then set this instance to AV extracted. That is by right clicking on this, you are supposed to set this as AV extracted. If I click AV extracted, now you can see just by clicking on this, whatever the capacitance and resistance which are being extracted, that is parasitics, are being included here. Then save your design. Now after saving, you just click open. It will open the schematic window. Can you see here, just it is test NAND underscore test is the cell name, this is the view name, it is the configuration view. Then if I descend down this symbol using descend edit option, then you can see AV extracted view, because we have set that as AV extracted. Earlier it was schematic, now it is AV extracted view. That means now it is ready for the post layout simulation. This NAND symbol will be incorporated with all the R and C values now. Now in order to simulate this, follow the same procedure. Launch the ADE window. Then if I launch the ADE window, then if I have already saved the state, just I am going to load it. If I load, I can see I am doing the transient analysis, and the signals which are to be plotted are A, B and Y. Post layout simulation can be executed by running netlist and run. It's going to show the waveforms. Then here, in order to calculate the delay, invoke the calculator by executing tools calculator option. Then select delay function. The delay function for the two signals, signal 1 should be input A and signal 2 should be output Y. Then observing the inputs, if we want to calculate the delay between this edge and this edge, input is falling and output is rising, and falling edge is edge number 1 here for the input, and for the output it is rising for the first time. Therefore we can consider the edge numbers as edge number 1 for the input and it is falling, and edge number 1 for the output and it is rising. Then clear the buffer, apply these arguments, then evaluate the buffer. It's going to show the delay as 50.74 picoseconds, which is higher than the previously calculated value for pre-layout simulation, which was 36 picoseconds. To compute the delay for the remaining 3 combinations, this edge we need to consider in the input, that is rising, and it is first rising edge, and for the output we need to take the corresponding edge as this. It is falling edge and it is first falling edge in the output. Hence, in the calculator, we need to keep edge number as 1 and it is rising for the input, and similarly for the output, edge number 1 and it is falling. Clear the buffer and apply these arguments, then evaluate the buffer. The delay is going to be 158 picoseconds, which is more than the previously computed pre-layout values, that is 155 picoseconds. Then for the next delay calculation, we need to consider this edge and it is falling, and in the falling count, it is the second falling type. This is the first one, this is the second falling, and the corresponding edge in the output is this. It is rising and it is the second rising edge. Hence, in the calculator, edge number should be 2 for the input and it is falling, and for the output, edge number is 2 and it is rising. Clear the buffer and apply these arguments. Evaluate the buffer. It's going to be 166 picoseconds and it is more than the previously computed value. Then for the last combination, observing the waveform, I'll be taking this edge here, which is rising, and it is second rising edge in the input, and the corresponding output is this edge, and it is falling and it is second falling edge in the output. Hence, in the calculator option, edge number will be retained as 2 itself. Only the edge type for the input is rising and for the output it is falling. Clear the buffer and apply these arguments. Evaluate the buffer. It's found to be 74 picoseconds. This completes the delay computation after doing the layout, that is post layout values. Obviously, the results obtained after that is for post layout simulation will be more than the pre layout simulation values. That's because we are including the R and C values for the simulation. This completes the back annotation process. Once the back annotation is done, final step is convert your layering information into data stream, that is a language which a foundry people can understand. For doing that, the procedure I will be explaining now, that is the conversion of the layout information into graphical data stream form. For that, first step is go to your CDS log. In that file, in the CDS log window, file, export, that is I am trying to export my layout information into the form of a stream. Click on file, export stream. If I execute, it will initially all this will be blank. I am supposed to give the name of that stream out as NAND, that is it is user defined NAND.gds. GDS stands for graphical data stream. Then after this, library you need to select, that is by browsing, it is my library test. Then this is the name of the cell and this is the view of the cell layout. Then if I say apply, it's going to convert the layering information into GDS to graphical data stream information interchange format. Once it is done, it is going to be shown in a separate window which will display the layering information in a format which it can be sent to in which we can send it to fabrication. Once it is done, it is going to display it is completed. Then if I say yes, this is your GDS2 for the NAND gate. It is showing, it is the stream file is NAND.gds, that is for cell name, and the extension is GDS. Top cell is NAND and view is layout, and it is giving the information of all the layers available in your design in the form of in a format which a foundry people can understand. This is just a stream information.